Good morning, everyone. Today we'll be presenting on deadlock detection and recovery in operating systems. I'm Nandini Patni along with Zehra Fatma and Ashmit Vedant. We'll explain what deadlocks are, why they occur, and how operating systems detect and recover from them in order to maintain smooth performance. A deadlock occurs when two or more processes are stuck, each waiting for resources held on by the other. For example, one process holds a printer and waits for a scanner, while another holds a scanner and waits for the printer. Deadlocks happen because resources like memory and input output devices are limited, and processes often hold one while requesting for more. If not managed, this leads to frozen processes and wasted CPU time, which is why handling deadlocks is vital for system stability. There are four conditions required for a deadlock to occur, called Kaufman's conditions. First is mutual exclusion, where only one process can use a resource at a time. The second is hold and wait, where a process holds onto a resource while waiting for the others. The third is no preemption, resources can't be forcibly taken away. And finally, there is circular wait, where processes form a loop, each waiting for another. When all four exist simultaneously, a deadlock can happen. There are four main strategies used by an operating system called prevention, avoidance, detection, and recovery. In prevention, the system eliminates at least one of the four conditions in order to ensure deadlocks aren't occurring. In avoidance, the OS checks each request to keep the system in a safe state, often using Banker's algorithm. Detection allows deadlocks but identifies them using algorithms, and recovery resolves them by terminating processes or preempting resources. Our focus today is going to be on detection and recovery. In detection, the system does not try to stop deadlocks from occurring, but identifies them once they happen. For single resource instances, the wait for graph is used. If there's a cycle, it indicates a deadlock. For multiple resources, the detection algorithm uses matrices like available, allocation, and request in order to check which processes can finish and which are stuck. This approach allows high resource utilization, though it adds some system overhead time.
Now let us start by understanding the wait for graph, which is an important tool used to detect deadlock in operating system. In this graph, each node represents a process and a directed edge that shows that one process is still waiting for another to release the resource. If there is a cycle in the graph, that usually means a group of processes are waiting for each other, and that indicates a deadlock. For example, P1, P2, P3 forms a cycle, which means they are in a deadlock situation. Now let us look at the deadlock detection algorithm using matrices. First, the allocation matrix shows that each process what it currently holds. Second, the request matrices that shows that each process still what they need, and the available resource shows what's left in the system. When we apply the algorithm, we find that only process 3 can finish, but process P1, P2, P4 are unable to complete even after their resources are released. So this means a deadlock is detected among process P1, P2, P4. Once a deadlock is detected, the next step is recovery. There are mainly two recovery strategies. First, process termination, where one or more processes involved in a deadlock are aborted to free the resource. Second, resource preemption, where resources are taken away from some process and is given to other. Both methods aim to restore the system to a stable state. Now let's go deeper into process termination methods. There are two main approaches in this process termination method. First, abort all the process. This clears the deadlock very quickly but causes a big loss of work and is only used as a last resort. Second one, abort one process at a time. This minimizes the disruption but it needs a careful selection. The system can decide which process to terminate based on the criteria like priority, how it holds a resource, or termination cost. This helps to reduce the negative impact on overall performance.
Understanding resource preemption and its challenges. Resource preemption enables the operating system to reclaim resources from one process and allocate them to another to resolve deadlocks. However, it introduces several challenges: data integrity risks, the existence of non preemptible resources, additional overhead for state management, and potential starvation of low priority processes. Effective system designs must address these concerns while leveraging preemption for deadlock resolution. Example recovery scenario. Consider two processes P1 and P2 each holding a distinct resource R1 and R2. When P1 requests R2 and P2 requests R1, a deadlock arises. The system intervenes by preempting R1 and from P1 and reallocating it to P2. Once P2 finishes and releases its resources, P1 can proceed. This process exemplifies how the operating system resolves deadlocks to maintain system stability and process completion. Advantages and disadvantages of deadlock techniques. Various strategies exist for handling deadlock. Prevention eliminates deadlock but often restrict resource utilization. Avoidance dynamically manages allocations but requires system knowledge and increases overhead. Detection and recovery allows high concurrency, though at the cost of performance and recovery complexity. Ignoring deadlock removes management overhead but risks system hangs in rare cases. Summary. Deadlocks represent a critical challenge of operating system, occurring when processes are perpetually blocked, each waiting for a resource held by another. Four necessary conditions must be present: mutual exclusion, hold and wait, no preemption, and circular wait. Operating systems use detection algorithms to identify deadlocks and, once detected, employ methods such as preemption or process rollback to restore normal system operation. Thank you.